Welcome to Optimizing the Game Thread. And I firstly just want to say thank you all for coming. So in this talk, we're going to go over the basics of how to profile, where to start with profiling, and how we look at different tasks on the game thread and prioritize these based on sort of how easy they are and that sort of thing. So firstly, I'm Jake Simpson. I'm an associate lead programmer at Tanglewood Games. I've been in the industry about 5 years now. So for most of that time, I've spent working on gameplay systems for different projects. And then more recently, I've been looking at the platform and optimization side of things. And specifically with that, I've been leading a team helping optimize Quidditch Champions for Gen 8 consoles. So that's PS4, Xbox One, and Nintendo Switch. So, as I mentioned, I work for Tanglewood Games. This is led by Chris and Terry, and we help lots of different studios with their engineering needs. So, as mentioned, whether that's gameplay support, tools and pipelines, for which my colleague Angel did a great talk on yesterday, porting to different platforms, and then optimization. And these are some of the different projects we've worked on over the last few years. So, to go over what we're going to talk about today, I want to give some introduction to performance in general. So I'll go over some of that key knowledge you need to start optimizing. And then what the game thread is, what it does, what it's responsible for, that sort of thing. And then how we profile in Unreal. And for this, I'm going to focus on Unreal Insights, which I'll go over a bit more in that section. So then I'll get into the common issues and solutions. So with Tanglewood, because we work on lots of different projects, we see lots of different traces, and we see the common patterns that come up time and time again. So these are some of those patterns we found and how we go about fixing them. I've got a small section at the end on network optimization as well. Network optimization, everyone thinks immediately of the networking side of things, but there's also quite a bit of CPU overhead that comes from this. So I just want to briefly go over some helpful strategies there. And then hopefully at the end we'll have a bit of time for Q&A. Let's get started then. So some key numbers to know when looking at performance. You've got 33.33 milliseconds, and that's your budget for 30 FPS. If you want to go to 60 FPS, half it to 16.66. And on the newer hardware, we go even further to the 120 mark. So especially on the newer consoles, they've got sort of the performance mode versus the fidelity mode, and with this, you sort of might move that budget around depending on what needs doing and what exactly the budgets are for your game. But in this time, your game thread has to finish. And it's not just your game thread, you've got your render thread and your GPU as well. But the game thread is what we're going to be focusing on today. So this is Unreal Insights. As mentioned, this is what going to be the main focus of the profiling today. This is one of the main tools we use at Tanglewood for helping to optimize. So I'll break this down a little bit here. At the top here, we can see our different tabs. So if you're using Unreal Insights, to get a trace like this, you can use the console or the command line, use -trace equals, and then specify some channels. Using the default, you get quite a bit of information like we've got here. And depending on what different channels you might get more tabs in here. Your session tab there will give you some brief information about your trace. So your file path, your name, what channels you use to trace there. And then Time and Insights is going to be the main view we're going to be looking at today. So moving on to the next section there, we've got our frame window. And this is going to show us all of the different frames across the time period we've traced and shows the different timings there. And you can see how we've got the budgets on the left-hand side and our different frames are color coordinated based on that. And you can see how this is really useful for identifying where you might have some hitches in the project. For example, over here, we've got some sort of bigger spikes. We then move on to the main timing window, and this is where you're going to be looking for all of this optimization side of things. We've got our different threads, so you can see the GPU at the top there, the game thread, we've got RHI down here. We can scroll down this list and we've got lots of different sections. We've also got our timeline view at the top here where we can select a range of time we can use. This is essentially your call stack. So as you go through your different events, you'll see them pop up in here one after another as they get called. One of the main things to use if you want to get as much information as possible out of this is stat named events. You can use this on either the command line or in the console, but this is going to give you a lot of this data that you need here. We'll then move across to the right-hand side here where we get our timings and counters window. For this talk, we're going to be looking primarily at the timing window, and you can see we've got a few different columns we can look at here. So all the different events here are going to be the events we've got in that selected time period. We've got a count, how many of these there is in that range, and then our inclusive and exclusive time. So our exclusive time is just the amount of time spent in that singular event. So that doesn't include any events that get called by that, whereas the inclusive time includes all of that time of the events it calls as well. So you can see how the averages are a great place to look here. Moving on to the game thread. Game thread's the main thread where your logic for your game is going to run, as the name suggests. So you've got a lot of different things that run on here, and we'll go over all of this in a little bit here. But because this runs so much, we look at asynchronous work quite a bit here. So we've got a lot of different background threads we can use. So we could distribute some of that work from the game thread across those as background threads. We do that in a few different ways. So firstly, parallel for. This allows the other threads to run the same work as the game thread alongside it. So if you've got 100 tasks, you can split them 20 among each thread, and your game thread can keep running that work as well. You've also got a task graph system. So this is slightly different in the sense that game thread doesn't run that work at the same time. The game thread can go off and do anything else, work on a different system, whereas all of your background threads can work on these tasks instead. With asynchronous work, you do come into some hardware limitations. Firstly, depending on what platforms you're working on, there's different core count, which limits how many threads you can run asynchronously. So if you look at Switch, it's only got 3 cores. So you've got game thread, render thread, RHI, your background threads, your audio thread. You can see how you can quickly run out of cores there and run out of time. There's also the limitation of core affinity. So this can be sort of a more complex issue, but with certain platforms, they're pretty slow at switching threads between cores. So for Xbox One, for example, it's pretty slow here. So what we would do is set our core affinity so that game thread can only run on core 0, for example. And this means if it does get interrupted by another task that is a high priority, we're not moving that to a different core, which is going to take a long amount of time because we have to reload the cache, all that sort of stuff. And if we look at insights here, to look at our game thread specifically, we've got a little filter we can go to here and untick all the threads we're not bothered about. So we can quickly just limit this down to only the game thread, and then we don't have to worry about seeing everything else that's in there. So as mentioned, the game thread does a lot of work. If we look at the trace here, we can see how all of these different sections, there's lots of different things going on. And we'll go through some of that now. So if we zoom in right at the start here, we've got our input. The input usually runs at the beginning of our frame because that's likely going to decide what actually happens in our frame. We'll then move across slightly to our movement. And depending on what your game is, your movement might be in a slightly different place. If it's physics-based, it might be later on in the frame. But in this example, which I'm using Lyra for, it's fairly early on. And you can see with movement how there's the same event multiple times in here. And this is because when we move one actor, it then moves all of its components and anything attached to it, that sort of thing. So we then sort of end up with a chain of movement, which is why movement stands out quite a lot when we look at traces. With movement, we also have collisions, and this works in the same way by moving down that chain. So when we see the movement, we likely also see collisions there. What we tend to see on the game thread as well is a similar pattern of start tasks and finish tasks on the game thread. So if we look at our animation here, there's actually a section at the bottom here where we have an enqueue task, and this kicks off a task on the task graph to a parallel thread. So this is the start of our animation, and this runs on the game thread by default. And then if we move along and look at one of our other background threads here, we can see how all of this work is being done on an asynchronous thread. And this is kicked off by that start task we were looking at a second ago. And then once this is done, it kicks off back to the game thread for an animation completion task. So that pattern of the start on the game thread, run the logic on the async thread, and then come back to the game thread is something we see a lot across animation. We see it with Niagara too, with our system on the game thread, kicking off to our work on an async thread, and then we also come back to this on the game thread. We also see this with physics. I don't want to go through all of these here because there's loads of them, and I'll leave some for you to find yourself. But then at the end of our frame, we also have slate. So this is where we run all of our UI. We take all of our widgets, run all of our invalidations, slate animations, all that sort of thing. Sometimes when we look at timings of the game thread, we see that we've made a lot of optimizations, but actually our game thread time hasn't dropped. And this is something that we see pretty common. And if we zoom in here, we can see that we've actually got some of these wait for task events. And this is because although we're running a lot of work on the async thread, our game thread's actually run out of work to do by this point. So it's just waiting till they finish. And we see these quite a lot at the end, towards sort of that end of our physics frame here. So the best way to identify what these are waiting on is to just highlight the end of this frame here. So we can highlight that section and scroll down until we see an event that roughly lines up with the end of that. And we can see here we found a Niagara system task that's running asynchronously. And we can see there's actually quite a bit of a time difference between that finishing and the end of our event. And that's because there's another event in there, which, as I mentioned earlier, is the NQ task. So this is where we're sending work back to a different thread. And as mentioned, with Niagara, we run that asynchronously, and then when it's finished, we run back to the game thread and tell that to finish up the work. So if we scroll back up to the top here, we can confirm that actually, yep, that's a Niagara system instance finish task. So we know that that was likely the task that was just finished there. So we can take a look at another quick example. If I just grab another wait for here, again, we can see that the task that finishes after is Niagara, and just below us there, we've got our Niagara task there. So from this, we can identify that either we need to run those Niagara systems earlier in the frame, so they get finished before, or we need to optimize these specific systems we can see on here. And that's a great way to identify that actually it wasn't the game thread that was slow, it's actually the work we're distributing. Profiling in Unreal, as you saw, there's lots of different events you can see in Insights, and a lot of that is marked up by default in the engine. But when you start to add your custom code, you want to make sure that appears in Insights too. So we want to make sure we've added the right profile tracking for what we need. So a few different ways of doing that. We've got quick scope cycle counter, declare cycle stat, and scope cycle counter. And these are macros that are defined in the engine. So if you're in C++, you can define this like this, and you give it a stat name. So that stat caller function we can see there, I've defined it in our function. We can see it appear in our timing window, and then again in our Insights graph. The difference between these different stats is quick scope cycle counter is good for one-off events. So this caller function only really makes sense in this function. Whereas if I had something that I wanted to run in, say, every function of my actor, I'd use the declare cycle stat to declare it once at the beginning of our file, or wherever it makes the most sense. And then I'd scope that in each of the functions. So that allows you to reuse these stats across multiple places. One thing to keep in mind is there is a profile and overhead. So depending on the type of profile you use, it samples things slightly differently. But you will also see a little bit of overhead because of these macros. So because these are sort of running some extra work to make sure they appear in Insights, you'll see a bit of a profile and overhead there that will make your events look a little bit longer. So there's some guidelines we make sure to set when we're profiling at Tanglewood. And these are great sort of just in general to make sure that you're getting the most out of your profiling. So firstly, use a broad range of data. This means don't just look at one frame, because you never know, another frame might have a completely different sort of set of priorities. And don't just look at one platform. As mentioned, depending on your hardware, you can run into many different issues. So make sure that you're looking at different platforms to prioritize sort of the most valuable tasks there. The same with playthroughs. Depending on what the player does in your game, it might drastically vary what actually happens on your game thread. So you want to make sure you use a couple of different playthroughs and sort of find out where your best data will be. Running your configurations as well, depending on how you package your build, is also important. If you're trying to profile your game build, you don't want to be using the editor. There's a lot of overhead there that comes from the editor. So make sure you're using a package build. And with this, try to use test. Test will give you much more accurate numbers, as it strips out a lot of that development logic that isn't needed. You can use development if you're needing to step through code, breakpoint it, that sort of thing. But if you're getting Insights numbers, try to use test as much as possible. And where possible, use automation. If you can automate the playing of your game, you know that every time you run this test, you're going to see the same numbers. And if you can make this deterministic, even better, because you can use that for A/B testing. Check that one change list against another. Actually, this change that's just gone in has increased our game thread time a ton. Let's back it out and take a look what's happened there. So to get into our main bulk of things here, we'll look at ticking, and I've mentioned that a couple of times now. But what is a tick? A tick is an update function that gets called every frame. This is used in most programming and software, but in Unreal that's controlled by an ftick function. So this is a struct that's used in the engine to define that an object wants to tick. And this is automatically registered for each actor and component with the primary actor tick and primary component tick respectively. Each actor, object, actor or component can have multiple tick functions associated with it, so you're not just limited to those primary ones. You can set up multiple different ones depending on what you need. So tick functions have a couple of different parameters on them. The first one I'm going to go over is the tick groups. And as mentioned, we've got sort of a physics tick portion of our frame. So if we zoom in here, we've actually got this pre-physics tick group. So this is before we kick off any of our physics logic. And this is the first tick group you can assign to in your tick functions. Moving on, we then have the start physics. And start physics is where we kick off our physics logic. So with that start task we mentioned earlier, that's where that starts off. We then have our during physics that runs along that asynchronous work of our physics. And then the end physics over here, which is where we usually see a lot of these wait for tasks. And we see that because certain components and objects, like Niagara or skeleton mesh components, can't finish their tick function until the end of until their finalized task has come back from the asynchronous thread. Which is why we end up with sort of sections like this, where we wait until one of those tasks finishes, quickly run on the game thread, and then we're back to waiting again, waiting on these other tasks. Once you get past the end physics, there's also a small post physics here. And depending on what's actually happening in your game, depends on what might go in these different sections. But in Lyra, this post physics is pretty small. Beyond that, we then have some code that you can't really jump into with tick groups. Your tick groups ends at post physics. So this is just some extra work that runs sort of after that main physics tick there. And then beyond all that, we've got our slate tick that was shown earlier. So again, we've got sort of our pre-tick, our sort of pre-pass, and then our main sort of draw of slate. So do our objects need a tick? If we look at a trace like this and we identify it, there's a lot of really small lines in our trace there. And when we look at the time down here, we've got 22 of them, and they're taking 44 microseconds. It's not a lot of time there. But when we zoom in on those, there's actually quite a bit of overhead. So all of these ticks we can see were really small. They've got really small hierarchies. They're not calling other events. But when we zoom in, we can see how not only is there an overhead between all of these tick functions, there's an overhead within the function itself. So the execute task has got a bit of an overhead, the tick function task has got a bit of an overhead. So this can quickly add up. So we can disable that by default. If we're in C++, we can change our primary actor or primary component tick to switch off the can ever tick. We can also register this if needed, but most of the time it's not too needed. If we're in blueprints, we can turn off the start with tick enabled. And even better, if you go into your project settings, you can turn this off by default. We also have the widgets, and widgets have a slightly different ticking method. So the blueprint widgets you've got will have two different tick modes, never and auto. So if it never ticks, it never ticks. You don't have to worry about it. But if it's set to auto, it goes through some calculations to determine how it should tick. So if it's got slate animations or it's got latent blueprint actions, it will tick on demand. So this means it'll tick when it's running those animations or latent actions. However, if you implement the event tick node in blueprints, it will tick every frame. Even if you've got nothing connected to that event tick node, it will still tick every frame. But let's say we don't actually implement that event. We don't have any animations, we don't have any latent actions, but we still see in our trace that a widget's ticking. And the reason for that is if you've got a base C++ class to your widget, if you don't add the disable native tick metadata in there, the code doesn't know that you haven't implemented the native tick in C++. So it will make sure to tick anyway, just in case. So if you don't want your widget to tick, drop that in your U class. That's going to help. And this doesn't get passed through to the child classes. So you'll have to implement this in sort of each class of your hierarchy. So if we take a look back at our trace here, we can see how those 22 instances of 45 microseconds, we've dropped down to nothing now. Because we didn't need them, they weren't ticking. However, sometimes it's not that simple. And if we look at this section here, we've still got lots of those small events. But actually, sometimes we're actually doing some work. So we need to take a slightly different approach here. So if we've got a slightly different tick size, depending on what's happening, we can utilize the tick interval on tick functions. This is another parameter I mentioned earlier. And this allows you to specify how often you should tick. So if you set this to 1, it'll only tick once a second. If you set this to 0.5, it'll tick twice a second. That sort of thing. But again, sometimes it's not that simple. Sometimes you need to run something every time the player jumps, for example. You've got no way of knowing that. So you can implement something a bit more adaptive so that you can modify your tick interval based on whether something's happened or not. And ideally, you'd use an event-based system, and this wouldn't need to be a thing, but event-based systems aren't always possible. So if we're looking at our tick interval, very similar to our beacon of a tick, we can modify this on our primary actor or primary component tick, or in our blueprints, again, we've got our tick interval there just before start with tick enabled. So that's nice and quick to change, nice and easy. However, if we want something more adaptive, we'll have to implement something similar to this, where we check a condition. If that condition is valid and it passes, we say, okay, well, what we needed to happen has happened. So let's reduce our tick interval because we want to tick more often, make sure we're catching them updates. Whereas if it hasn't happened, we might want to extend the tick interval. So waiting for the player to jump, they didn't jump this frame, so check in 2 frames. They didn't jump that frame, so check in 4 frames. But actually they jumped this time, so drop back down to 1 frame to make sure we're catching any subsequent jumps, that sort of thing. The issue with this is it can introduce some latency. So you need to be really careful about how you use this. But it can be really powerful, depending on what you need. There's also some Unreal systems that help with reducing this tick interval. And if we look at the significance manager, this is a framework that you can implement to help reduce the tick interval and other parameters on your actor, depending on whether it's relevant or not. And you can implement these relevancy rules to determine whether it's based on distance or size on screen, visibility, all that sort of thing. So you've got complete control there. It is a framework. You have to implement this yourself. There's also the animation budget allocator. So this allows you to set a budget of milliseconds depending on how much time you want to spend on the game thread for your animation. So again, this is just game thread work. It doesn't count as that asynchronous work we have with animations there. So any animation blueprints that aren't as relevant, it will drop the animation rate down for them. So they'll run at a lower frame rate, they'll interpolate, or they'll stop completely if your budget's low enough. As I mentioned, there's some overhead of a tick, and that's really noticeable if we look at a trace like this. So here we've got 18 different objects of the same type running consecutively one after another. It's taking about 2.8 milliseconds across all of those events. So how would we solve that? Well, we'd look at tick aggregation. And anyone that's looked at tick aggregation has likely seen John's talk from Sea of Thieves. It's a great talk. If you want to look at tick aggregation, definitely check that one out. But when would we want to aggregate our tick? Well, we want to aggregate our tick when we've got many instances of the same object, either running together like we had in the frame there, or they might also be separated across the frame, which tends to be sort of the case we see more often in profiles. So for this, all we want to do is we want to create one singular tick function that's going to run all of these objects instead of each one running it individually. So this is going to bring them all together under one tick function, because that tick function is going to run and then call all of the consecutive functions one after another. And this is going to help reduce the cache misses. So this is the time it's taking to load that object's data into memory, that sort of thing. And there's a great talk by Andreas about the cold hard cache, the cache simulator. And there's a plugin you can actually download for an Unreal cache simulator. So the second part of tick aggregation allows you to extract some common functionality. When you've got all of those objects running one after another, if they're all doing the same logic at the start, you can extract that into your tick function, pass that data in instead. You can also batch your logic, which means you run the logic much less often, instead of running it sort of once per object. So again, if we look at elbow 4 here, those 18 objects we've got running at 2.8 milliseconds, we can aggregate them, and this is just pulling them together, reducing the cache misses and reducing that overhead of the tick tasks and the sort of time between, and we drop down to 0.95 milliseconds there. So you can see that saved us nearly 1.5 milliseconds just from taking us there. Tick aggregation is a solution that you'll have to implement yourself in many cases, but at Tanglewood we're working on a plugin for the marketplace to help speed this up for you. So keep an eye on our social media, and hopefully that'll be ready soon. The other portion is combining work. So if we look at movement here, as I mentioned earlier, movement can be quite heavy. And we've got movement twice here, where we're moving the same object twice. And that means moving all of its components and attached actors. So what would we do here? Well, with movement, this is a common problem, and especially so in multiplayer games. If we look at fast-paced multiplayer games, we need to update the movement from the server, run any correction, smooth it out for the client so it's not as noticeable, and then predict where we want to be from the client in the next frame. So that's 3 potential movements we're doing there. So to combine that, we'll look at deferral. So instead of directly setting the movement and the new location every time we do that movement, we'd cache these all into a single value so that we modify that value, and then we set it at the end of the frame or whenever makes sort of the most sense for your game. And that means we're only running that logic once, and we're only running it when it's needed. So we can combine these 2 events, where we're setting 2 different movements, into one, just by sort of combining that and deferring it a bit later in the frame. So what other patterns do we see? Well, it's going to seem pretty simple, but light versus heavy logic. If we look at canvas panels used to be the default widget in all of our UMG widgets, and they're really heavy because they're a one-size-fits-all widget. They've got sizing, alignment, Z ordering, sorting, all that sort of thing. So if you don't need all of that on every widget, switch to an overlay or a grid panel. Let's say with UE5, this isn't the default anymore, so it's much easier. But reducing the use of canvas panels can help save a lot of time there. This is a bit more awkward. It takes a lot of manual work. It can be quite slow, but it can save you quite a bit of time in your slate tick. Slate animation is also a big one. When we looked at the insights capture earlier with Slate, there was an ECS cost event at the start. And that ECS is the sequencer system being brought into Unreal, into the Slate tick, because we were running Slate animations there. Slate animations are very heavy because of that sequencer. So instead you can use logic-based animations, use some looping timers and that sort of thing. It's a bit dirtier, but can save a lot of time because you're not bringing in that sequence cost. The alternative approach that is much better is to use materials. If you use materials for your animations instead, you've taken that cost completely off the game thread and putting it onto the GPU, which is great. There's also distance checks. These are a small one, but if you're doing simple distance checks, just checking sort of if actor A is closer to actor B than C, you can use a distance squared check instead. And you might have to square one of your values to do this distance check, but it ends up being a lot cheaper than having to do a square root. So switching these over throughout your game, especially for logic you're running very often, can save a little bit of time there. And again, these are all very manual processes that can save a little bit of time. So these are things that we'd leave sort of later in the project when we're sort of running out of those easier tasks. If we take a look at the canvas panel here, I put together a quick example, and you can see the S-constraint canvas here. That's our canvas panel, and that's the overhead we've got of it there. So if we look on the left, we've got a canvas panel widget. So this is just canvas panel with a widget inside of it, also has a canvas panel, and it's just flashing on and off. We also have exactly the same widget using overlays instead of canvas panels. And you see how there's no event there for overlays because there's not as much overhead. There doesn't need to be one. But looking at the time there, we can save around 50% just by switching over from canvas panels to overlays. And that's not going to scale sort of relatively to our bigger widgets, but it can show the overhead that canvas panels actually cost, even on a small widget like this. Blueprints versus C++, also a very hot topic. There's a big misconception that blueprints are a lot heavier than C++, and they are heavier in the sense that the cost comes from the function call. So each node is a function call, so the more nodes you've got, the more cost it's going to add, and there is the overhead that comes from blueprints. But that doesn't mean don't use them. They're great for designers, tech artists, that sort of thing, to get in there, quickly mock things up, and get things working. That takes a lot of the engineers. So make sure you're using them, because they're not that bad, and you can optimize them. If you are looking at blueprint time specifically in your trace, you want to look at the blueprint time stat. So if we look at that here in our trace, we can see how these highlighted events are all our blueprint time. You can see how we're taking around about half a millisecond there, just spent in blueprints. And we have 95 different blueprint time events here. So that's likely 95 different blueprints we're using in this single frame. So if we want to look at optimizing our blueprints, one approach we could take is nativization. So nativization is great because you're converting that blueprint to code, but it is very manual, takes a lot of time, and it has some issues. So in Unreal 4, there was the automatic nativization method in Unreal for exclusive and inclusive nativization. So exclusive meant you specifically said which blueprints you wanted nativizing, whereas inclusive was the opposite. It nativized everything but what you specify. In Unreal 5, this has changed a little bit. So they now have the blueprint header view. So this instead just generates a single header for you. So it generates all of your function signatures, your variables, and you have to implement the C++. This is still very manual. The old system instead ran on Cook, which meant you couldn't really iterate on it. It wasn't human readable. So it's a better approach, but it's still very manual. It's also high risk. If you convert a blueprint to C++, maybe you make a mistake somewhere. It's easy to do. We've all done it. So it's best for the original creator of the blueprint to either switch it to code or work with you switching it to code. And this is going to make sure that it's definitely doing what it's doing before and after you make that change. So some of the things we see in blueprints a lot, pure nodes. Pure nodes aren't that bad, but if you do things like this, so that it can really add up. So we've got a pure function there, and we're taking off that function 3 times to 3 different pins. This means we're going to execute that function 3 different times, and likely going to get the same result back every time. This also happens with reference parameters. Sorry. So if you've got a C++ function, you've got some reference parameters that are all out variables, you're going to see the same thing here. If you've got 1 return value and 2 out references, you drag once off each of them, you're still calling that function 3 times. And if you return a struct instead and break that from there, you're still calling that function 3 times because it's going to evaluate that struct 3 times. For loops work the same with pure nodes. So if you've got a for each loop like this, you drag in our get array. That array we know has 100 elements in there. Well, we're going to call that get array 100 times. This is the same for regular for loops. If you're using the length and getting the last index, again, you're going to call that 100 times. And that might not be a massive issue if you're just returning a local variable or a member variable. But if you're doing some heavy calculation in there to get an actor and pull data off it, that can really add up. So how do we go about fixing that? Well, we just cache it. If you cache it into a local variable, you can use that as many times as you want. You've only called that function once. Really quick, really easy. And that's what non-pure functions do. So they create a local variable behind the scenes that you can't see and essentially do the same thing. Something we also see in blueprints a lot is select nodes. And select nodes aren't that bad. And this goes for both the sort of select float nodes with specific types as well as the wildcard node. And select nodes aren't that bad. But if you're using an instance like this where we've got a local variable, quick, cheap, easy, and that's used 95% of the time, then we have a longer calculation here that we only use 5% of the time. Well, what's actually happening in our select there is it's evaluating both of those inputs, no matter which one we choose. So even though we're only using that calculation 5% of the time, we're evaluating it 100% of the time. So quick, simple solution to that, switch over to a branch. Just using a Boolean check, you can quickly see that our executions are only going down one path. So we're only going to ever evaluate that calculation when we need to evaluate it. So it's these quick sort of solutions that are going to save you that little bit of time here and there. As mentioned, I want to quickly go over some network optimization here at the end. And if we look at the dedicated server here, I'm going to focus on dedicated server because listen servers can vary depending on your game. But with a dedicated server, they're usually single core. And this is because you don't need a rendering, so you're just running all your game work. And we have them single core so that we can run as many instances of these on sort of a server farm as we possibly can. So what happens on the CPU with networking? Well, it needs to check every single marked parameter to see if it needs replicating down to the client. It also needs to pack any data it's sending via client and multicast RPCs, and unpack any data it's received via server RPCs. If we move on to the client, again, that has to unpack that data that's been sent down from the server, and it needs to pack any data it's sending up to the server. So there's little bits of things that happen here, but that can quickly add up. So how would we improve that? Well, we can switch to push model, and push model is going to help reduce that time we spend checking all of the different marked parameters, because push model means that is on you. You specifically need to mark your properties as dirty when it needs replicating down. So the server doesn't have to do any of that anymore. You can also switch to using network dormancy. And network dormancy allows you to set actors and components as dormant and not check those for replication right now. If they're at the other side of the world, you don't care whether it has changed color, for example. But as the player gets close, that might be something you want to switch back to awake and make sure that you're getting that replication again. Array serialization and delta serialization are a massive topic, but if you look at the fast array serializers in Unreal, you're going to see how these can really help speed up your array replication from the server to the client and vice versa, because it's only going to replicate down what elements of that array it needs to, what's actually changed in there. And we've also got quantization. Quantization is useful for reducing the amount of data we're sending. So with types like f-vector, we can limit these to only sending to 1 decimal place, for example, because we don't need it to be that accurate. If you're looking for more detail on these optimizations, you can check out this talk here. This is a pretty old talk from UE4 about server optimization, and it sort of covers both the network and the CPU side of things. So it's a great talk to look at for any more detail in these areas. But that's everything I've got for you today, so thank you all for listening.